Okay, section 2.6 is related rates. Related rates problems find the rates of change of two or more related variables that are changing with respect to time. So these are sort of the word problem applications for section 2.5. So we'll start out with, so what that means is, what if we have like a conical tank, and it's filling up with water. So there are some things that are changing in this. One is the volume's changing with respect to time. And another thing that's changing is the radius of the water is changing with respect to time. So we would have a dV dt, the rate that the volume is changing with respect to time. And we also have a dr dt, the rate the radius changes with respect to time. So we'll be solving some problems like that. The very first thing, though, we'll do is example 1. Variables x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. They are both differentiable functions of t. That means we can take the derivative of x with respect to time, and we can take the derivative of y with respect to time. So they're going to ask us to find dy dt when x equals 1, and given that dx dt is 2 when x is 1. Okay, so we have an equation and it's differentiable. So we're just going to take the derivative of these variables with respect to time. So the derivative of y is 1, but the variables don't match, so it's dy dt equals the derivative of x squared is 2x. The variables don't match, so it's multiplied by dx dt, and the derivative of 3 is 0. Okay, so this is our problem. Now we're going to plug in everything we know. They want us to find dy dt, so that'll stay our variable. X is 1, and the value of dx dt is 2. So dy dt is 4. All right, let's get an example. This is example 2 in your book if you want to look at it. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So you drop a pebble into that pond, and it starts to ripple out. And all of these circles are concentric circles, which mean they all have the same center, which is where that pebble first went in. I'm just going to get rid of my picture. As shown in figure 2.34, so they've got a better picture for you. The radius of the outer ripple is increasing at a rate. Let me just write this down. Okay, the radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So let's slow down and take it one step at a time. The radius, you can kind of read through these prepositional phrases, is increasing at a rate of, so the radius is a rate of 1 foot per second. Now that's not the radius, that's the rate the radius is increasing. So that's our dr dt, the derivative of the radius with respect to time. But that's supposed to be a t down there. And now read on. When the radius is 4 feet, so r is 4, at what rate is the total area A of the water changing? What is the rate of the area? At what rate is the area changing? So they want us to find dA dt. Now you need an equation that relates A and R for circles. So you might think of area equals pi r squared. So that's a formula that relates the variables that we're talking about. And then we're ready to do implicit differentiation. Derivative of A with respect to time is dA dt. Pi is a constant. The derivative of R with respect to time is 2r dr dt. dA dt we don't know. That's 2 pi times the radius, which is 4, times dr dt, which is 1. So that is 8 pi. And then to get our units straight, this is area, so it's measured in square units. So it's feet squared per, and let's see, what were we doing? That should not be a 1 foot ds. That is a rate of 1 foot per second. So that should just be a second down there. So the unit of my rate the area is changing with respect to time is 8 pi feet squared per second. So the top of page 150, there's this nice box, and it says if you are given the verbal statement, the velocity of a car after traveling for 1 hour is 50 miles an hour, they're calling x distance. So the distance is changing is 50 miles an hour, so they're calling that dx dt, and the time is 1 hour. And the second one, water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. Huge hint here as to what we're talking about. Volume is measured in cubic units. So we're talking about the volume in the pool, and it's being pumped in at a rate, that's a dV dt. A gear is revolving at a rate of 25 revolutions per minute. 1 revolution is 2 pi radians. So that's the angle. 1 full revolution or 1 full angle measure is 2 pi. And we're revolving at a rate, that's the rate that the angle is changing. So theta would be our angle of revolution. So the rate would be d theta dt. Last, a population of bacteria is increasing at a rate of 2,000 per hour. That's the change in the bacteria per time. So if x is the number in population of the bacteria, dx dt would be the rate of 2,000 bacteria per hour. Okay. One last question we'll do together here. Example 3. Air is being pumped into a spherical balloon at a rate. Okay, this is the last example we'll do together. Air is pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 1 foot. So now back up to the beginning. We're talking about a sphere at a rate of 4.5 cubic feet per minute. That's the rate that the amount of air in the balloon is changing, and that's a measure of volume. And your huge hint for that is cubic right there. So the volume is changing with respect to time is 4.5. Find the rate of change of the radius. They want us to find the rate the radius is changing when the radius is 1 foot. So we have we've listed out all the different information they've given us and what they want us to find. Now we need we need an equation that will tie together volume and the radius for a sphere. And I will give you these formulas on the test, and for your homework, ones that you don't know, you could Google. So the volume of a sphere is 4/3 pi r cubed. And we're ready to do implicit differentiation. So dv dt equals the 4/3 constants times the derivative of our radius with respect to time. And dv dt is 4.5. 4/3 pi times 3. That's 12/3, or just 4 pi. R is 1 squared. We're trying to find dr dt. So 4.5 equals 4 pi dr dt. Divide by 4 pi. And we don't like leaving decimals in a fraction. You might change that 4.5, that 4.5 to 9/2. And you already have a 4 pi down there. So you might make that 9/8 pi. You might just turn it into a decimal and round it. The book did both. So the radius is changing with respect to time is 9/8 pi. We need to get our units. Radius would be feet per minute. Okay, so our homework is going to be on page 163. And I will list that for you on Facts or on Google Classroom.